In our previous session, we had seen about landing performance. Let us move on to turning flight in this session. Let us now consider some cases involving radial acceleration which leads to curved flight path. That is, let us consider the turning flight of an aircraft. We examined three different cases, that is, a level turn, a pull up, and a pull down. Under level turn is illustrated here. The wing of the aeroplane is banked with angle phi and at angle phi to the vertical. The bank angle phi and the lift L are such that the component of the lift in the vertical direction equals the weight. So L cos phi is equals to W. And therefore, the aeroplane maintains a constant altitude moving in the same horizontal plane. However, the resultant of L and W leads to a resultant force Fr which acts in the horizontal plane. This resultant force is perpendicular to the flight path, causing the aeroplane to turn in a circular path with a radius of curvature equals to r. From the force diagram, the magnitude of the resultant force Fr is equals to root of L square minus W square. A new term called the load factor is defined here, which is N is equals to L by W. The load factor is usually quoted in terms of G's. For example, an aeroplane with lift equal to 5 times the weight is said to be experiencing a load factor of 5 G's. Hence, which can be written as Fr is equals to W root of N square minus 1. Now the aeroplane is moving in the circular path at velocity v infinity. Therefore, the radial acceleration is given by v infinity square by r. From Newton's second law, we have Fr is equals to mv infinity square by r, which is equals to w by g v infinity square by r. Combining these two equations for radius of curvature r is equals to v infinity square by g root of n square minus 1. The angular velocity is equals to g root of n square minus 1 by v infinity, which is also called the turn rate and is given by v infinity by r. For maneuvering performance of an aeroplane, both military and civil, it is frequently advantageous to have the smallest possible r and largest possible angular velocity. From these two equations, which show to obtain a small turn radius and large turn radius, we want the highest possible load factor, that is highest possible L by W, and the lowest possible velocity. Now let us consider another case of turning flight, that is pull-up, in which the aeroplane initially in straight level flight where L is equals to W suddenly experiences an increase in lift. For this pull-up maneuver, the flight path becomes curved in the vertical direction with the turn rate is equals to d theta by dt. The resultant force Fr is equals to L minus W, which is equals to W into n minus 1. From Newton's second law, we have Fr is equals to mv infinity square by r, which is equals to w by g v infinity square by r. Combining these two equations, we have radius of curvature is equals to v infinity square divided by d into n minus 1. Hence, the turn rate is equals to g n minus 1 by v infinity, since turn rate is equals to v infinity by r. A related case is the pull-down maneuver illustrated in the diagram here. Here, the aeroplane is initially flying at a level flight, suddenly rolls to an inverted position such that both L and W are pointing downward. The aeroplane will begin to turn downward in a circular flight path with a turn radius r and turn rate d theta by dt. By an analysis similar to those preceding, the following results are obtained. That is, radius of curvature is equals to v infinity square by gn plus 1 and the turn rate is equals to gn plus 1 by v infinity. By this, I hope you would have understood the turning flight for three different conditions. Let us move on to Venn diagram in the next session. Thank you.